So we have the battery, we have the light bulb, and if we want to connect those, if we just connected them as positive terminal of battery connected to the one side of the light bulb, and also positive terminal of the battery connected to the other side of the light bulb. In that case, if you take a look at this loop, this loop passes through the light bulb, but it does not pass through the battery. So the battery isn't really part of the loop. And have you seen how you would write out an equation for a circuit like this? In general, what sort of equation can you always write out for any complete loop?
Change in voltage equals 0.
Yeah, the total of all of the changes in voltage for a loop like this have to add up to 0. And this is, ultimately, this is very similar to the Bernoulli equation in some ways. Voltage is basically the electrical version of energy density. The main difference is when we're talking about fluid flow, what do we mean by energy density? And that was energy per unit of what?
Volume.
Yeah, energy over volume. That is, if you've got some sort of fluid moving around, you're talking about how much energy the fluid has divided by the volume of the fluid. Or to put it another way, how much energy, how many joules of energy per cubic meter of fluid. For electricity, though, we don't have fluid flowing through the wires. What's actually moving around within the wires?
It's like the electric charge.
Yeah, these charged particles, the electrons. And so instead of trying to measure the volume of electrons, which would be kind of nonsensical, we're basically just treating them as single points. Instead, we're talking about how much charge worth of electrons. We're measuring the amount of charge measured in coulombs of electrons. So the electrical equivalent of this, energy density, is not energy over volume, it's energy over charge. That is, how many joules of energy per coulomb of charge. So that would be the units there. Joules per coulomb. Or J over C, joules per coulomb. So that's what we mean by energy density for electricity. And as an abbreviation, we call that electrical potential or voltage. So this is what voltage means. When we talk about the voltage, we're just talking about the energy density, how much energy per unit of charge. And the abbreviation for joules per coulomb is volt. So 1 volt literally means 1 joule per coulomb. So for instance, a battery, like this battery, for example, says 9 volts on the side. 9 volts literally just means 9 joules of extra energy per coulomb of charge. As current flows through a battery in one terminal and out the other, the charge that flows through, each coulomb of that charge gains an extra 9 joules of energy. So that's really what a battery does. What a battery does is it creates a boost in energy density, a boost in voltage. And usually that's thought of as corresponding to a difference between the terminals. You'd have one terminal at a low voltage, that is low amount of energy per coulomb of charge, and the other terminal at a high voltage, lots of energy per charge. And the voltage label on the battery, in this case 9 volts, is just the difference between the low voltage zone and the high voltage zone. So that's really all the battery does. It creates a difference between a low voltage zone on one side, the negative terminal, and a high voltage zone at the positive terminal. And the delta V of the battery, usually written as epsilon, is just how much difference there is between the voltages. And that's very similar to what thing in a fluid flow? What sort of device in fluid flow gives a boost to the energy density?
The pump?
Yeah, the pump provides a boost to energy density. In fact, if you take a look at the Bernoulli equation for a pump, the delta energy density per volume, or delta pressure, would be some constant related to the pump. A battery does something very similar. For the battery, instead of a delta pressure, though, it's a delta voltage, because voltage is the energy density for electrical flow. Delta voltage is some constant. And we usually write that constant as the Greek letter epsilon. 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 Okay. So the battery just provides a constant plus epsilon, much in the same way that a pump provides a constant plus work density of the pump. So for instance, if we're talking about this difference between the low voltage zone and the high voltage zone, we would presumably call the low voltage zone usually V equals 0. And the high voltage zone would be V equals positive epsilon. In the case of this battery, it would be 0 volts and 9 volts. So that's really what the battery does. The battery just provides this distinction between a low voltage side and a high voltage side. Any questions on that so far? And for mapping out voltages, I find it really useful to color code the voltages. Like, let's say we color this high voltage zone red and this low voltage zone blue. If we fill that in, like this region is at this high voltage. And the region on the other side is at a low voltage. But the thing is, we also have these wires. If you have another point along the same wire, what should you expect about the voltage, let's say right here? If you're just going through wire, what should you expect to happen to voltage?
Voltage would stay the same if there's no...
Yeah. That's really the most important attribute of wire. Delta voltage for any wire is going to be 0. And that's not entirely true. Realistically, wires do have a tiny bit of resistance, but it's so small we can basically ignore it. You can treat wire as being like the electrical equivalent of wide, smooth pipe that's easy for fluid to flow through. So one end of the wire and the other end of the wire and every point along that wire all have the same voltage. All these locations are at that same high voltage, positive epsilon. So all these locations are at that same high voltage. And based on the way we've connected the circuit here, all of these points are also at that same high voltage. So here the voltage is also positive epsilon. And what do you notice about the voltage on one side of the resistor and the voltage on the other side of the resistor?
They're both high.
What was that?
They're both high voltage.
Yeah. There's no reason, there's no side that's higher voltage, no side that's lower voltage. Both sides of the resistor are at the same voltage. And what does that suggest? If there's no difference in voltage, what does that suggest about the resistor? Or to make another analogy to fluid flow, let's say you've got a pipe. And let's say you have
just 0.
Sorry, what was that?
Is the resistance just resistor just going to be 0 because
it does have resistance, because resistance is really a property of the object itself. Like this light bulb has a certain amount of resistance, even if nothing's happening to it. Resistance is basically a measure of how difficult it is for current to flow. In the same sense that a section of pipe has resistance, even if there's no fluid flowing through it right now. But let's say you have a pipe that has, let's say, a high pressure zone on one side and the same high pressure on the other side. Would you expect current to flow through this pipe? Or if not, what would have to be happening to make current flow?
Does it have to go from high pressure to low pressure?
Yeah, let's say we do have low pressure on the other side. We would expect current to flow from the high pressure zone to the low pressure zone. And this goes back to the idea of the Bernoulli equation. If we've got these 2 points, if we're comparing those 2 points, your Bernoulli equation would have a delta pressure. There's no change in cross-sectional area, no change in height, so we don't have any other types of energy density. There's no pump, so what would be the only thing we'd have on the other side of the equation?
Would it be resistance?
Yeah, we've got that resistance term, negative I times R. So the pipe itself has resistance. That's a physical attribute of the pipe and the fluid that's in it. There's a difference in pressure. We can expect that difference in pressure to cause current to flow. And we should expect current to flow from the high pressure zone towards the low pressure zone. So that's what the Bernoulli equation tells us about this pipe. That if there's a difference in pressure, we should expect current to flow from the high pressure region towards the low pressure region. Whereas if there was no difference in pressure and no other differences like height or cross-sectional area, we should expect no current to flow. And we can do the same idea with the resistor. The resistor is like a pipe with resistance. It's just the electrical version instead of the fluid version. And much like a pipe with no pressure difference shouldn't expect any current, a resistor with no voltage difference shouldn't expect any electrical current. Because the difference in voltage is what causes current to flow. If there's no difference in voltage, if both locations on both sides of the resistor are the same voltage, there's no reason for current to flow. So conceptually, we can say that this resistor, this loop experiences no current because the resistor is not getting any voltage difference. And it turns out that for an electrical resistor, the formula for delta voltage is exactly equivalent to this formula from the Bernoulli equation for delta pressure. Specifically, the delta voltage for a resistor, instead of pressure, we have voltage. Instead of fluid current, we have electrical current, but it's still written as I. Instead of fluid resistance of the pipe, we have electrical resistance of that resistor, but it's still written as R. So for any resistor, that's going to be the delta voltage, as opposed to a battery, which has a constant delta voltage, or a wire, which has no delta voltage. So these are really the important voltage drop formulas, or delta voltage formulas. Battery provides a constant amount of voltage difference, specifically a boost in voltage. Resistor provides a drop in voltage that's not constant. Instead, it's proportional to current. That is, the faster current's flowing, the more voltage drop there is. Or to put it another way, the more different the voltages are, the more current will flow. And then a wire provides no voltage difference. Any 2 points on the same wire will be at the same voltage. Any questions on that so far? So this arrangement, as we saw, does not provide any current at all. But if we rearrange things a bit, how could we set this up so that it will cause current to flow? How would we have to connect things differently?
Attach the low voltage and the battery to the resistor.
Yeah, if we take the other end of the light bulb and attach it to specifically the negative terminal of the battery, now if we fill in the rest of the voltage map, we can say this entire wire is going to be at the low voltage. All these locations marked in blue here on the bottom side, those are all going to be at 0 volts instead of at positive epsilon volts. Which means that if you take a look at one end and the other of the resistor, the light bulb, We've got one end at plus epsilon volts and the other end at 0 volts. That means there is a difference in voltage across the resistor, the light bulb. So what does that tell you is going to happen?
Current is going to flow.
Yeah, current's going to flow, and specifically it's going to flow from where to where?
From high voltage to low, so the red
Yeah.
to the
Exactly, from the high voltage zone towards the low voltage zone. And we also have the continuity principle here, the idea that current in must equal current out. It's usually called the junction rule when we're talking about current, electrical current. For any point, the total current flowing into that point must equal the total current flowing out of that point. And that's true for any single location on the wire, or even any larger region on the wire. But in particular, let's say we're taking a look at this corner. The current flowing in one side must match the current flowing out the other side. So that means we have to have the same amount of current flowing through this branch. And if we apply the same principle to the next corner, the lower left corner, the current flowing into that point must match the current flowing out of that point. In fact, at every point on the circuit, every point on this loop is going to have the same amount of current because there's only one path. There's nowhere else for the current to go. So this is essentially the same principle as the continuity principle for fluid flow. If you've got some pipe, the fluid flow current flowing into the pipe must match the fluid current flowing out of the pipe. Same thing for electrical current. For any section of wire or any point in the wire, the current flowing into that point must match the current flowing out of that point. Any questions on that so far? And the reason we write that as a summation of current flowing in must match the summation of current flowing out, is that we often use this, and this is the reason why it's called the junction rule. We often use this applied to junctions where several wires come together. Like let's say you've got a wire that splits into two paths. And let's say the currents are labeled, let's say we've got current flowing in, and that branches off into these two directions. If we label those, let's say I sub 1, I sub 2, and I sub 3, what can we say about these three currents? How would those have to be related to each other?
I1 equals I2 plus I3.
Exactly. Considering this junction, the current flowing in is I1, current flowing out is I2 plus I3, so those have to match. Current in must equal current out. Which means if you know any two of those currents, you can immediately find the missing third one. So that's usually called the junction rule. It applies to any location in the wire, but it's most often used at junctions where a wire splits into several wires or where several wires come together into one wire. So that's often useful for getting one more equation. If you know everything about the circuit, except for maybe there's a couple of currents you don't know, and you don't have enough information, the junction rule can often be used to get one more equation to get a system of equations that you can solve. Also, while we're at it, let's take a closer look at current. Still written as I. But if we compare this to fluid current, how are we defining fluid current in the first place? Like if you say the current is, if you say the current flowing through a pipe is 3, that would be 3 what? What is current actually measuring for fluids?
Is it like meters cubed over seconds?
Yeah, it's usually measured in meters cubed over seconds. Meters cubed is measuring what sort of quantity?
This volume.
Yeah, fluid current is defined as volume over time. More formally, delta volume over delta time, in the sense of how much volume flows past this point per second. So that would be the units, cubic meters per second. Whereas if we're talking about electrical current, again, we don't want to try measuring the volume of the electrons that flow past. What property of the electrons do we measure instead, though? How would you describe how much electricity is flowing past?
Change in volts.
Voltage is more like the pressure, though. It's how much push there is. But if you just have some clump of electrons, instead of counting up the electrons or trying to measure how much space they take up, what's another attribute of the electrons that could be measured and described? What's the most important property electrons have that we care about?
Charge.
Yeah. So instead of talking about how much volume flows past a point per second, or instead of talking about the number of electrons that flow past the point per second, we talk about how much charge flows past this point per second, charge over time. And charge is usually abbreviated as Q. Sometimes capital Q, sometimes lowercase q, depending on the textbook. But charge over time, how much charge worth of electrons flows past that point per second. And so that's going to be measured in coulombs per second, also known as amps, abbreviated as A. So that's the unit of measurement for current. Amperes, or amps for short, equals coulombs per second. So that's the unit of measurement we use for current. We might say the current is 20 amps, for instance. That would be one example of a current. And that's just describing how much charge is flowing past each point per second. So current is describing how fast the charge is flowing in terms of how much charge flows past per second. Whereas voltage is more of a push. It's the electrical equivalent of pressure. So the voltage is the push that makes current flow through the circuit. Any other questions on that so far?
So, you were saying that fluid needs push, but electrical doesn't need a push. Is that what you're trying to say?
For fluid flow, the push that makes it happen is pressure. That if you've got a pipe, you've got to have a difference in pressure from one side to the other to make fluid flow. The electrical equivalent of that would be voltage, that you need a delta voltage to make current flow, to make electrical current flow. Let me sketch that out real quick. So in here, if you have a pipe, like just a section of pipe with fluid in it, if you want fluid to flow, what difference do you have to make that flow happen?
Change in pressure.
Yeah, you got to have a difference in pressure, high pressure at one side, low pressure at the other side. So let's say you've got high pressure at one side, low pressure at the other side. And that's going to cause current to flow, fluid current, from where to where?
From high to low.
Yeah. The difference in pressure causes fluid to flow from high pressure zone to low pressure zone. And what would be the equation describing that?
Change in P equals negative IR.
Yeah. So that would be the simplified Bernoulli equation for that specific case. It's essentially saying the more pressure difference you have, the faster current's going to flow. But also the more resistance the pipe itself has, the slower current is going to flow. Because R is a property of the pipe itself here. So I should probably label that as well. The pipe has a resistance. So that's the core idea of resistance for fluid current. For electrical current, instead of a pipe, we have a wire, presumably a wire with some resistance. So this wire's resistance is also going to be written as R. Just keep in mind that means electrical resistance, not fluid resistance. So a very similar concept, but it's going to have different units of measurement. And what has to be happening here to make current flow through the resistor? What difference has to exist?
Change in voltage.
Yeah, you got to have a high voltage at one side and a low voltage at the other side. So that difference in voltage is equivalent to the difference in pressure for the fluid circuit. The difference in voltage is going to cause current to flow. And again, that's going to flow from where to where?
High to low.
Yeah, from the high voltage zone towards the low voltage zone. So that's current. And it's still called current, still labeled I. It's measuring a different thing. It's measuring how many coulombs of charge flow past per second instead of measuring how many cubic meters of volume flow past per second. But it's still a rate of change in what's flowing over time. So it can still be analyzed in exactly the same sort of way. And the equation relating those is almost exactly like this simplified Bernoulli equation. It's just that instead of pressure, we're talking about voltage. Instead of fluid current, volume per second, we have electrical current, charge per second. And we also still have times R. It's just that here R is the electrical resistance of this section of wire instead of the fluid resistance of this section of pipe. But even though the variables have different meanings and different units of measurement, it's the same structure. And this relationship is usually called Ohm's law. So these two situations, even though they're fundamentally different things, these are still following the exact same pattern, the same sort of behavior, so they can still be modeled with the same sort of equations. Any questions on that so far?
If we have time, can you go over the difference between series and parallel resistors?
Yeah. First, let's take a quick look at this circuit, this single loop numerically, and then we'll see if we can complicate that. Because if you have a single loop, we can use going back to the idea of the loop rule, that the voltages have to add up to 0. We can use that to construct an equation and actually find the current. Because the current, I was just making up 20 amps. But let's say we know the battery's voltage and the resistor's resistance. Resistance is typically measured in ohms, which is same ohm as in Ohm's law. For units of measurements, voltage, of course, is in volts, current is in amps, and resistance is what's called ohms, which is abbreviated as a capital Greek letter omega. So 1 ohm means 1 volt per amp. So it's ultimately just an abbreviation. Anytime you see ohm, the omega there, you can always replace it with volts over amps and vice versa. Volts over amps can always be replaced as ohms. And that's just the unit of resistance, how difficult it is for current to flow. So let's say, for instance, we have resistor whose resistance is, let's say, 30 ohms. And let's say that battery is 9 volts. That's enough information to solve for current, because if we set up the loop rule, in this circuit, if you go around a complete loop, like, let's say we start at the lower left corner and go around a complete loop. What things have you passed through as you go through that loop?
A battery and a resistor.
Yeah, so that means our delta V for the loop will be delta V of that battery plus delta V for that resistor. And those changes have to add up to 0. We can always replace delta V of the battery with plus epsilon. And we can always replace delta V for the resistor with minus IR from Ohm's law. And we know epsilon, we know R. How would you solve for I here? How would you isolate current?
Can you repeat the question one more time?
In this equation, if we wanted, because we know epsilon, that's 9 volts in this case, we know R, that's 30 ohms. If we wanted to know the current, how would you algebraically isolate I here? Like before we even plug in any numbers. Yeah, if we just add IR to both sides, and then what else would we need to do?
Divide by
R.
Right. So that means the current is just going to be epsilon over R. In this simple loop of a single battery and a single resistor, current is always going to be voltage over resistance. And in this case, if we fill in those values, epsilon is 9 volts, R is 30 ohms, 9 over 30 reduces to 3 over 10 or 0.3, and volts over ohms ends up being amps. So 0.3 amps would be the current. This entire loop has 0.3 amps of current at every location. That describes how fast charge is moving in terms of coulombs per second. Any questions on that so far? All right, then let's take a quick look at that idea of series versus parallel. The main idea there is that series means that the resistors are sort of one after another along the same path. For instance, if you've got several resistors that look like this, and it's not so much about what they look like. The important thing is how they're connected. If these are all connected in such a way that they have to be on the same path, like let's say you start going through one of the resistors. If your path takes you through one of the resistors, let's say you travel through resistor 1, is there anywhere else you can go? If you travel through the first resistor, what's the very next thing you're going to hit?
Second resistor.
Yeah, you hit the second resistor. There's no way you can avoid it. That's really the important thing about series. Series basically means if you go through one of these resistors, any one of them, you have to go through all the whole set. There's no way you can go through just one of these resistors and bypass the other. Even if it's in some more complicated circuit, maybe there's many branching paths. These 3 resistors are arranged in such a way that you can only go through either all of them or maybe take another path and bypass them and go through none of them. So series means it's an all or nothing. You either go through all these resistors or you take some other path and go through none of these resistors. That's one way to tell for sure if these are in series. If the resistors are arranged in such a way that you have to go through all of them or none of them, then they're in series. And one of the important things about those, since that is just one path, what does that tell you about the current through these resistors? If you think of this in terms of, sorry, what was that?
Were you asking us if each of them were 1/2, what would the total be?
No, just about in terms of the current. Like let's say you have some current flowing through the first resistor. We've got current flowing through the first resistor. We've got current flowing through the second resistor. We've got current flowing through the third resistor. And we might label those, for instance, I1, I2, and I3. But what do you know about how those currents are related? For example, if you were to
just all
apply,
add them up.
sorry, what was that?
You add them all up. That's how they're related. If current goes through one of them, you have to add 2 and 3 as well.
We wouldn't exactly be adding all these currents together. But if we try applying the junction rule to some point, like let's say we just choose a point between the first two resistors, the junction rule says that the current flowing into that point must match the current flowing out of this point. What's the current flowing into this point, and then what's the current flowing out of this point?
The current flowing in would be I1, and the current flowing out would be I2.
Right. And according to the junction rule, for any single location, the current in must equal the current out. So that tells us I1 and I2 have to be.
They're both equal.
Yeah, I1 and I2 are the same. And likewise, we could draw a point here and say the current in must match the current out. So I2 has to equal I3. In other words, all three of these currents are the same.
Couldn't you have like a small resistor next to a big resistor though?
Yeah, these resistors could be different resistances. Maybe you've got like 100 ohms and 3 ohms and 5,000 ohms. They all have to get the same current because there's only one path. If there's only one path, the current flows along that entire path and there's nowhere else for it to go. I find it's very useful to think of current almost as being like a bicycle chain going around the pedals and the gears. The current would be like the number of chain links that pass by per second. If you look at one spot on the chain and you see that there's 10 links passing by per second, and you look at another spot on the same chain, it's also got 10 links passing by per second. Same thing here. You've got the same number of electrons flowing past per second, no matter which point on the wire you look at. So that's one of the most important attributes of resistors in series. All these resistors have to get the same current because they're all the same single path. There's nowhere else for the current to go. Whereas if you had like a branching path, you've got current flowing in, some of the current goes this way, some of it goes this way. But if you just have one path, all the current is flowing along that path and there's nowhere else for it to go.
So with the change in voltage, is that what would change after each resistor?
Yeah, the voltages are going to be different because if we take a look at voltage, delta voltage for a resistor is the usual negative IR. And that's true for each one. And we know they all have the same current, but they could have different resistances. So each one has its own delta voltage. And the delta voltages we can actually add up. Because the first resistor, like let's say you start at high voltage on one side and you have low voltage on the other side. In fact, let me call this, let's say we call this very high voltage. And then the other side presumably is very low voltage. Currents flowing from the very high voltage side towards the very low voltage side. But if we go through one of the resistors, we are losing some voltage. So in this in-between zone, we'd have, let's say, kind of high voltage. And then you go through another resistor, you lose some more voltage. So you get to, let's say, kind of low voltage. And then you go through one more resistor, you get to very low voltage. So each one of these resistors is associated with a certain amount of loss of voltage. In the same way that as you go through a pipe, each segment of pipe causes a loss of pressure. But all the voltages would add together to get the total drop in voltage. So let's say the very high voltage, just to throw some numbers in, let's say the very high voltage is 100 volts. And let's say the very low voltage is 20 volts. Overall, there's a loss of 80 volts. The three resistors in this case would have to split up that available voltage. Maybe through the first resistor, and I'm just making up some numbers here. Let's say you lose 50 volts, so you're down to 50 volts. And then through the next resistor, you lose another 25 volts, so you're down to 25 volts. And then through the last resistor, you lose 5 volts. So you lose 50 volts, then you lose 25 volts, then you lose 5 volts. Overall, you've lost all 80 volts. But the resistors are splitting up the available voltage. So these, I think, are probably the 2 most important properties of resistors in series. If the resistors in series, they all get the same full current because it's flowing through all of them, but they have to split up the available delta voltage. In parallel, it's the exact opposite. In parallel, all the resistors get the same full delta V because they're all branching from the same starting point, the same ending point, but they have to split up the available current because it's split up at a junction. And we can take a look at more examples of that next time. Any other quick questions before I go?
Thank you so much.
Yeah, you're
It
welcome.
helped a lot going over this.
Oh, also one other thing, if you go to math.ncheese.org/P7B, I'll paste that in the chat. There should be a link to Intro to Electrical Circuits. It's just a list of a whole bunch of the relevant information about the important quantities, the units of measurement, how they're all related to each other, and a basic introduction to the idea of series versus parallel as well. So take a look at that, math.ncheese.org/P7B, and then click on Electrical Circuits Intro. I think that'll be a good overall introduction to the important topics. So take a look at that, and I will see you next time.
Thank you.
You're welcome.
Thank you.